All right, up next we have Christopher Couch, who's actually a 3-time MIT grad, so bachelor, master's, and PhD. He's currently the Senior Vice President and Chief Technology and Procurement Officer at Cooper Standard, the global automotive supplier, as well as the founder and CEO of Liveline Technologies. Liveline was an outgrowth of the innovation activities at Cooper Standard, and it's a software that provides real-time process control of factory systems using self-trained AI agents. Chris is actively managing as CEO and Chief Data Scientist. In addition to his AI and machine learning specialties, he also has gritty shop floor fluency in Japanese from his 7 years in Japan with Toyota, part of his total 12 years at Toyota. So welcome, Chris.
Thank you. Clicker. Great. Okay, thank you. Do we have any current students in the audience? Greta? Okay. I got some bad news for you. You just heard I was here for quite a long time on campus, and still when I come back decades later, I have the same feeling. Oh my gosh, did I forget my problem set, and do I have a quiz today? So maybe your mileage will differ, but that's my experience. The trauma is real, but I'm thankful for a lot of things I got out of here. Mainly my wife, I think, but the education was also good. So I'm going to talk mostly today from the viewpoint of one of my hats, which is the CTO of a public company in the automotive industry. Because I think really for this audience, the journey to how we got to what we're doing with the startup is really the interesting point. I'll leave time for Q&A. If you want to talk tech, we can talk tech. If you want to talk startup stuff, we can do that too. But I really wanted to take you on the journey that got us to where we've landed. A word about the mother company, if you will, Cooper Standard. It's a global automotive supplier. It's a small to medium-ish sized company in that industry. It's about $3 billion in revenue, give or take. And primarily they make global, fluid and sealing systems for vehicles. That's a very exciting space, despite the fact that it sounds very boring perhaps on the product side, because as cars electrify, they have a greater quantity of fluid thermal management systems than you would find on a gasoline car. And that's all stuff that we make. So that side of the business is booming and quite interesting from a tech standpoint, as well as just the development of the market. Most of what we do at Cooper Standard is continuous flow manufacturing, a lot of polymer stuff, some metallics. And I bring that up because that really motivates the problem we went to work on, which is this, and that is how do we automate complex multi-stage factory systems for improved outcomes given some of the constraints that I'm going to talk about in a minute. This is a picture from an example of a line. It's quite long. It's probably the better part of 200 meters, multiple stages of extrusion processes and heating and cooling and coating processes and more heating and more cooling and different treatments. And these run at fairly high speeds. You would find these types of extrusion lines running anywhere from 10 meters a minute to, if you're doing fiber optic cable coating, which we are with Liveline now, 500 meters a minute, right? So moving pretty fast. And the tolerances are very tight. These are systems that are making products carrying fuel, for example, or brake fluid. You can't have any leaks or pinholes, right, in hydraulic systems if you're extruding metallic tubes and coating them with different protectants. So that's sort of the physical context. And here are the design criteria that we had to work with. So first, it has to be fast to deploy. Why is that? Because a plant can have hundreds of SKUs, and the products change all the time. And the inputs to the products change all the time. Everyone, I'm sure, has heard about supply chain issues the last couple of years. It's been quite real. We've had to do many substitutions of polymers, for example, some of them quite specialty in nature that are not easy to find replacements for, and swapping them in and out as things become available. And that effectively changes the physics of the line, and it needs to be tuned for better control, right? So if we can't keep up with our control system design and tuning with that dynamic environment, we don't have a solution, right? This is not a refinery where maybe you can design a system that you sort of set and forget for 5 years. It's very dynamic. Has to execute fast. These are high-speed processes. Our control loops are running at about 1 hertz. That's the frequency at which we're making modifications to temperatures and pressures and RPMs and that sort of thing, right? So fairly high speed. So we don't have time to go off and run, for example, a simulation-based control like you might find in a refinery. We just don't have the execution time to do it. And also, that drives a lot of decisions about how you transform the data stream, right? Because we have to create features to feed our models, but we don't have time, right? So, we might have 100 milliseconds after all the transport in and out is done to build a feature set to pump into the model, get an answer, detransform, and then issue commands out to the line, right? So fairly aggressive. And then the accuracy is high. We're talking about 100 micron level, give or take, of accuracy at speeds of not 100 meters a second, 100 meters a minute, right up to order of 1,000. We're working as high as 500 right now, so order of 1,000, right? And then in terms of computational efficiency, this is where things really got interesting, because you've heard many times today about data. SKUs are churning so fast, we will never be able to wait months to get enough data to train with certain types of paradigms. So we had to develop a way to do this so we can model with a relatively sparse amount of data and get a solution that was good enough to execute controls. And then finally, data efficiency, that was data efficiency. And then computationally, right, we can't let things train for days and days and days. We have to have the ability to simulate and or model that we can turn and burn really overnight if we need to. So that was sort of the design criteria. And then we went through an evolution for the better part of 2 years on the solution. And we started off the way you might think, given that I'm a controls engineer. I'm not going to say old controls engineer. All right, maybe headed that way, but old school, right? So we got a bunch of hotshot classical controls people. We were doing complicated nested, PID loops and cascades of PID controllers, and it took us about 3 months to tune for one SKU, and it worked really well, right? But the design criteria, right? Not going to be a tractable solution for us. So we said, no problem, right? It's a physical system, it's multi-physics, there's chemistry, right? There's a lot of thermal stuff, there's gravity and tension on the line, no problem. We're just going to simulate it all, right? And do it that way. And that lasted about a month before we realized that there's no hope of pulling that off at the speed that we need to do it. And then we said, great, we'll do a partial ML-based approach where we will simply learn the physical model of the system because it's too complicated to build the big simulation with the Sol systems, and they actually laughed at us when we asked them about it. And so the idea was we'll train a neural net to simulate the physics of the line, and we'll put that into a classical controls loop that will then tune, right, and make it run. That, for a variety of reasons, turned out to be not a good solution either, although not for lack of trying. We had beautiful external models that were hooked into Simulink and MATLAB and trying to use controls design tools, and it doesn't work very well. So don't ever try to do that. So finally we said, look, let's just go all the way and try to do it with a pure ML-based approach. We can learn the physics model and we can learn a controls model, right? That surely must be a thing that we can do. And as CTO of the company, I engaged 2 different enterprise AI companies to work on this in sequence, and they both failed. And we weren't able to get a solution. And this is despite the fact that those teams were stocked with a lot of great talent, right? In Stanford, PhDs in data science. They had the second best, unfortunately. Come on, the Stanford joke. But they couldn't do it. And it came down to sort of the approach, right? They had paradigms in their heads about how to do this sort of modeling, and it just wasn't tailored enough to our problem. So when the last engagement failed, we said, look, we're going to either do this ourselves, we're going to solve our own problem as engineers, or it's not going to get solved, and we'll wait 5 years, maybe somebody will show up with a good solution. So I started to put together a team, and one of the things that I learned through all this was how to put together that team, right? We heard about talent a minute ago, and we have learned a lot about how to hire data scientists and software engineers. But one story I'll tell you that I think is interesting when I decided to sort of take this in our own hands, I put out a job posting as Cooper Standard Automotive Company for data scientists. And the month, how many applications did we get? Yeah, there it is. I see the zero over there. Zero applications, right? And the salary was solid, right, for the job and everything. We just couldn't figure it out. We're near Ann Arbor, Michigan, not a bad place, right? Surely there's at least some Michigan graduates that want to do this stuff. And hey, go blue. So we decided to go ahead and set it up as a startup company, first and foremost because of the talent story. We set up the company in February of 2020, a month before COVID. Timing's everything. And put the job posting back out as Liveline, and in the first week we had 200 applications. Only because we called it a startup in AI, right? Then we had to learn how to filter those people to find the good ones, but that's another story. So we set up this thing as a company and really essentially smashed our head against the wall for a good year until we thought we knew how to do it. We learned a lot from the enterprise AI companies. And what I mean by a lot is we learned 2 ways to not do it, right? Which is extremely important. And finally came up with a way. The reason that we persevered through this whole journey is because intuition says it's tractable, right? It's a physical system. We're not modeling irrational consumer behavior, right? Or something that's, who knows what the quote physics are. Real systems, right? They're complicated, they're multi-physics, they're nonlinear, actually, in a lot of cases. You're dealing with flows of different things through dies, and if you turn one dial, other stuff goes haywire, right, in a nonlinear way. But it's tractable, must be solvable, right? And that sort of kept us sane and willing to smash our heads against the wall for quite a long time. So here's what we came up with. This is fairly generic, I guess, but it'll give you the idea. We are running online inference and control, right, a real-time control loop with reinforcement learning agents as the controller, right? I'm running that in a 1 hertz loop. And you see on the right, it's talking to a PLC. We are completely agnostic about the PLC. We developed our own proprietary streaming platform that lives on top of that. And that platform then, or tapped into it, resides a suite of services, one of which is our RL-based controller agents, right? And there's some alarming services and some safety services running to make sure nothing gets too crazy. But we had to build that. And so that's all running in real time. The hardware to run it is very lightweight. We don't have specialized hardware in the plants. The controllers can, once they're trained, can run on a laptop fairly well. So we're able to do this with a fairly light footprint on premises. Getting there is a little harder, right? We obviously have to do a little more work to train these things. That data is shipped off. We do work in the cloud, and it's a 2-step modeling process. We actually use a previous generation of language models as the physics engine. And the intuition is we have multiple signals coming in, right? We're interested in the last minutes of data typically. That's a sequence. We want to predict the sequence of the multiple outputs that we care about coming up. It's a language problem. You're just speaking in sensor data. So it turns out language models are very good at this sort of thing. But the catch is we have that data efficiency issue, right? We don't have the data to go train, industrial controls GPT, right? Transformer architecture. We do have the data to train a little bit dumber version of language models that works really well. Right, so selecting sort of the right model for the job was a lot of it. Learning how to develop the feature set was a lot of it. We can, I can talk to you some details about that later if you want to. But I'll tell you now, we do a lot of work in frequency domain, right? It's part of the magic. So that's the physics model, and that gives us essentially an input-output model of the plant that we care about. That we then put into your reinforcement training loop, and we train agents to drive that to the outcomes that we care about in the facility, and it works really well. On reasonable hardware, and I mean, a GPU and not an A100, I'm talking about a desktop GPU that you might actually have. The physics model will train in 10 minutes, and the controls model will train in 2 hours. It's about where we are. And that's usually good enough performance to run controls. And notice I said good enough, because that's also part of the magic, right? This is controls engineering. We're not doing high frequency trading where we're concerned about losing millions of dollars if the decimal place is wrong. It has to be good enough to get us to the next iteration of the control loop where we're going to repredict anyway, right? So we're constantly predicting and repredicting and repredicting. So we care a lot about the predictions in the next minute. We don't care so much about the ones in 5 minutes. They're directionally correct, good enough. And in fact, mean directional accuracy is sort of our main criteria we look at when we train. If it's pointing the right way, we're bumping controls the right direction, we're probably in good shape. So that's what we came up with. Again, it's PLC agnostic. We interface to common industrial protocols. We built a bridge to do that. Our streaming service, for those that care about these things, is written on Kafka. Believe it or not, works extremely well for this problem. And the ML operations are highly automated. We don't have a single person in the company that is doing any modeling. They're working on advanced automation tools for the modeling at this point, right? We did a lot of modeling by hand, but we don't do any more. And so we literally have active hundreds of models right now that are controlling product production on 22 lines in 7 countries. And every night you come back and there's a menagerie that's been spawned out where we're doing back testing and comparing and figuring out if we need to replace versions of models. Very highly automated at this point. And hybrid cloud. So we do have a physical compute device on-prem to run the inference. The reason we do that is because this is industrial controls. We can't rely on an internet connection to run production, right? So we have redundancy even on-prem, and then of course the ability to do stuff in the cloud. A lot of the choices we made about the tech were all designed for speed, right? Speed of training and speed of inference and execution. And again, Q&A, we can dive into some of that if you want to. Rest assured, we went deep. We've extended TensorFlow libraries, right? We have written hyper-optimized stuff in C to do sparse kernel interpolation. It's been a very deep exercise to get us to where we need to be in terms of the execution, but we got there after a lot of pain. I'll show you some eye candy. So this chart is about the physics model, and the next one's going to be about the RL controls, right? Just to give you a sense of what we're doing. In this case, you have 4 outputs that we are concerned about for a product. Think about these as dimensions on something being extruded at high speed, right? The way to interpret these plots are there's samples going across the bottom. That's the steps ahead and into the future. We're predicting what the output of the plant is going to be given all the state variables that we're reading on. The black lines are observations, the red are predictions. You want to see those on top of each other. And these are samples of sequences, right? And then we're just overlaying them on the same plot as spark lines. And you can see that, especially in the first half of these, it's perfect, right? It lines up very, very accurately. The dimensions are normalized, but these are probably in tenths of a millimeter, I think, in terms of the physical measurement. So very good predictions. And this would be 10 minutes of training or so with, I should mention, maybe 2 days of data from the line. That's about what we need to get a good physics model. Will that encompass every possible situation? No, right? It's not self-driving cars where you have to understand all these crazy edge cases of people pushing strollers across the street at night and what have you. This is a physical production line, right? And so the philosophy is if things get out of a known band, you simply release the controls and the line goes back into manual mode and we call an operator over and they come and do what they do today, which is manage the dials of the line, right? And because these are predictive, we have typically minutes and minutes of advance notice that we will reach an uncontrollable state, raise the alarm, person gets over, we drop the controls out, and life goes on. Right, so much easier problem. Sometimes dumber is better, right? And certainly in this case, that's in terms of the AI, that's true. So that's physics. And then here, for those that have done RL, this may look familiar, right? This is an episodic reward plot. As it goes up, this is the RL agent learning to drive the line, right? And you'll see as we let it go, it gets better and better. The stopping question is an interesting one we can chat about in the hallway. And I can also tell you, too, that the lumpiness in this is over a year old, I think. Yeah, over a year old. We've taken a big step forward on that also, and have just started implementing a Bayesian framework that gives us much smoother performance up and about 5 times the conversion speed. And that's going live for us here this summer. So we've come a long way even on the RL side of things. And again, all of it is about speed of converging to answers for us. So you can see it learning, and it figures out how to drive. And then in our platform, we can back test that, of course. We can run it in shadow with actual production, but not closing the loop, so the people in the plants can get familiar with how it's making decisions. And then when everybody's happy about it, and we've demonstrated the performance stats would be improved, we close the loop and go live. I mentioned we're on 22 lines, 7 facilities now. Typically, we see scrap cut in half. We see line stops cut drastically. 80% is a normal number for us. We see operator touches dropping to almost nothing during the day, as you would expect, right? This is automation, and paybacks on the order of about 3 months for our customers. So very cost-effective way to do this. So that was all the CTO view, right, of us solving our own engineering problem. We believe that what we're doing has general applicability, especially in continuous industries. We know that now because we've gone to market with this, and we're working with external customers as of this quarter, in fact. We'll see where it goes, but so far so good. This is the team that did everything that I just showed you. That's it. That's the whole team. And we're supporting external customers at this point. And again, no data scientists are doing models. We're just doing automation at this point. And it's been a great pleasure, but also a lot of learning on how to assemble that team. I can tell you the team is about half modern data science and software engineers, and about half hardcore core gearhead controls nuts like me. It's been a fantastic combination to have people in the same room. And as somebody said, that's where the magic happens, right? Where you get the subject matter people in with the non. I will also tell you that to a person, the hardcore controls gearheads have learned how to be pretty darn good data scientists, at least interpreting things, and have learned to be pretty good developers as well. And I will also say we've had to teach the data scientists to be good software developers, because those 2 things are orthogonal. Sorry, it's the truth. So we think there's a big ocean out there for advanced process control, which is what this whole topic is called. It's not a robot, it's a system. That's old news and petrochemicals, right? If you go to Baytown, Wilkie mentioned it, right? There's the control room, and they have these systems that have models that are pre-built, they're tuned, don't touch it, right? And if you do want to touch it, we'll charge you a lot of money to bring engineers in and tune your system and be running test pulses through and all kinds of expensive things. So it doesn't work for small to medium industry. That's what we're doing. And we think that the economics of it makes sense for small to medium manufacturers. And there are a bunch of them in many kinds of continuous industries. Extruded rubber, extruded metal, wire and cable, textiles, thin film, some aspects of biopharm maybe. And that's where we're launching into as we speak. So operators love it, makes their jobs easier. They constantly tell us, don't turn it off. We have surprisingly had nobody say, are you trying to replace my job? Because in almost every place where we work, Mexico, Canada, US, France at this point, we can't run production because we don't have operators, right? That's really the problem we're solving with the automation, not replacing people. And so the people who are there are able to focus on, preventative activities and value-added stuff, thinking of improvements, what have you, and they love it, right? And this really is taking the drudgery of watching dials and turning, knobs all day long away from those folks. So off to the races. We do have some technical details. We don't spill all the beans, of course, but if you want to read more about the tech, go to that customerdocs.liveline.cloud, and you'll get an earful, all right? So I'm into Q&A now. That's it. Happy to talk about what's on your mind.
I think we have time for one question.
It's really bright. Hi.
Hi. It seems like you've done everything. What do you see as potential improvements in the next 10 years to what you have so far?
Many things, right? There are some things on the modeling side that we think are going to take us a next step up. I mentioned moving to Bayesian frameworks. That looks like a huge improvement for us. Time is money, right? Literally, paying Amazon money for web services too. That's a big step. We're doing a lot of work right now in automated scoring of incoming data to pre-select it for training. Most of the time, things run well on plants and the data is really boring. And giving more of that to the model doesn't really help it improve a whole lot, right? So we want to find the juicy bets, but we also don't want to feed it things that are completely insane. And I'm talking real talk here, like the roof leaked and there was a sprinkler spraying a sensor. I don't want that data, right? So we're doing a lot of work right now, and I will tell you that is a surprisingly hard problem to do right. And do right means that we validate it by training models and seeing if our data selection methods help get better models or not. It's surprisingly hard to do that in a purely hands-off way. Big area of work for us. A lot of work in developing better test harnesses for the controller models. Those that do controls engineering know there's a variety of ways to characterize performance, right? Obviously, getting good average part, characteristics is nice, but also concerned about things like settling times of controllers, about activity levels of the controller. These RL systems can be really jumpy. They like to make lots of little changes. Is that okay or not, right? How do we calm that down? Some of it is in the training itself, but there are other ways to address that. So there's a lot of topics around sort of controls theory. Stability is a great question as well, right? So there's some theoretical problems that we're still trying to figure out, as well as obviously just building and scaling at this point, right? We are at scale in terms of the data science side of this already. Not easy. I will tell you the two best hires that I have made on the team so far, and I'm not, my rest of the team hears this, don't feel too bad, but the two most helpful in terms of the company getting rolling is a world-class CI/CD person. We're fully automated in our code deploy at this point, and a great cloud ops person. I mean, those two people save our bacon and let a team of 9 act like a team of 30, right? Really important people.
All right, thank you so much. Appreciate you coming today. One more round of applause.
Thanks.